Alright guys, next up, halogenoalkanes. There's really only one reaction that we need to know, but this is where we have a single halogen on what is otherwise a saturated hydrocarbon. And the reason why this is reactive is because that carbon-halogen bond is really polar. Okay, so we have our carbon and then our halogen, X, whatever that is. It's really polar, and so our carbon is a little bit positive, and our halogen, whatever it is a little bit negative, slightly negative. And so we can consider this a carbon as electron deficient. Well, if there is a nucleophile floating around, it's going to be attracted to that electron deficient region. Okay, a nucleophile, that's a nucleus lover, something that's going to be attracted to positive charge. So these are electron rich, they're going to have a lone pair of electrons, they may also have a charge. And so what we're going to have is a nucleophilic substitution reaction where the nucleophile replaces the halogen. Okay? Specifically, here, it's going to be the hydroxide ion replacing your halogen, whatever X is. And you need to kind of think about how this happens. This is kind of neat. So, let's say we have, I'm going to make this bromine. Okay. Well, this bond is polar, so that your carbon is a little bit positive and your bromine is slightly negative. Okay. Well, if we have this in, say, a sodium hydroxide solution, okay, this is my nucleophile. That nucleophile is going to be attracted to that positive carbon. Now, bromine's rather substantial, but these hydrogens are rather small. And so the hydroxide is going to come in kind of from the back side, if you will. Okay. Now, what we're going to do is we're going to use what are called curly arrows. You're going to go, there's no curl to that. That's just a normal arrow. And it shows the movement of electrons. So I'm going to draw from the electrons on the hydroxide to the positive carbon. Okay. Now what's going to happen is that that's going to force this bond to break. So I'm going to draw an arrow showing from this bond, showing those electrons moving from that bond both to the bromine. And so what we're going to have temporarily, so much for my color coding, huh? Is we're going to have this high energy transition state. Okay. Of course, that's very unstable. Carbon's only going to bond 4 times. And what you get out of this is your alcohol group has replaced the bromine. Okay, so this is a means of how to make an alcohol from a halogenoalkane. Okay. Sorry. Alright, next up, benzene. Arenes are compounds derived from benzene. If something has a benzene group in it, benzene is going to be drawn shorthand like this. This is a phenyl group, so like go look on the back of your shampoo or soaps and you'll probably see phenyl blah 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 blah. That means that it has this guy. Okay, so benzene is C6H6. Michael Faraday figured that out ages ago, like 1825, but then they couldn't figure out, well, how is it arranged? And it puzzled everyone because it doesn't act like other unsaturated molecules. Or, you know, it doesn't have any isomers, and it doesn't undergo addition reactions very well. And if it just had double and or triple bonds, it would undergo those addition reactions, but it doesn't. So what actually happens is that it's a cyclic molecule where you have 6 carbons, each with 1 hydrogen attached. I encourage you, actually get a molecule kit and try and build this. Now that doesn't account for all the bonding, so people would draw it originally with alternating double bonds, and then they could draw this resonance structure, and that's not really correct. Okay? So the single bonds form this planar structure. Okay, they're called sigma bonds. And then the double bonds actually stick up above and below the plane of the rest of the molecule. And so you have this ring above and a ring below of delocalized electrons. Okay, there's a keyword, delocalized electrons. And this makes benzene a lot more stable than it should be. Of course, so now hopefully you can see why this gets turned into this as your simplified depiction for a benzene or a phenyl group. Okay, so there are several pieces of evidence that you need to know for this. The first is the bond lengths. All the carbon-carbon bond lengths are equal, and they're intermediate between single and double bonds. Okay, so if you look at the actual numbers, and so that lets us know that it's not just alternating double and single bonds, that there's got to be more to it. There's more sharing. Also, if we were to fully hydrogenate, excuse me, if we were to fully hydrogenate benzene, we get a value that's much less exothermic than we would think it is, meaning that benzene is more stable than it is. Okay, so that's known as the resonance energy, or the stabilization energy. And here's the idea. Delocalization minimizes repulsions between electrons, and thus making benzene a much more stable structure. So it lowers the amount of energy you would expect to need to hydrogenate it or do anything else. And since it's so stable, it is very reluctant to undergo addition reactions. It's only going to undergo a substitution reaction. In other words, we're going to replace the hydrogen with something, but we're not going to do anything else that, like an addition reaction that would disrupt those delocalized electrons. And lastly, if you have something like 1,2-dibromobenzene, you could rotate this, clockwise or counterclockwise all over the molecule, but all adjacent positions in the ring are equal. And so there's limited isomers, which again suggests this ring structure with the delocalized electrons. Okay, so the one substitution reaction that we need to know, is called electrophilic substitution. Well, we just said that a nucleophile was a nucleus lover, so an electrophile is an electron lover. Okay? Your electrophiles usually have a positive charge, or they're electron deficient. Okay, so the one that you need to know, the electrophile for you to know, is this little guy. So if we take benzene and we nitrate it, we're going to replace one of these little hydrogens. The hydrogen is going to be lost. There's a lot more behind this that you don't have to know for SL chemistry. You just need to know that it substitutes out and replaces a hydrogen, and this is your one electrophile to know. So there you have it.